Hello students. So in the previous video, we have discussed certain problems, that is finding HCF using Euclid's division lemma. So we'll get into the next concept where we'll be finding LCM. So we have seen what is HCF and we have seen what is LCM, and we have also seen how to find HCF of any two given numbers or any three given numbers. Okay. Now let's learn how to find LCM, least common multiple. Before that, let's look into a very important concept known as fundamental theorem of arithmetic. I repeat it, FTA, fundamental theorem of arithmetic. So what does this theorem says? You take any composite number, it can be expressed as product of primes. So what are prime numbers? What are composite numbers? Very simple. Prime numbers, composite numbers. Those numbers which have factors, which have only two factors, that is 1 and itself, are known as prime numbers. Those numbers which have more than two factors, for example, if I take 2, what are the factors of 2? In other words, the numbers which divide 2, which are those numbers that divide 2, it is 1 and 2 itself, which means this number has got only two factors. There are only two numbers that is going to divide this 2, which is that 1 and itself. If I take 3, which are the numbers that will divide 3? It will be 1 and 3 itself. There are only two factors, that is 1 and itself. There are no other factors, meaning there are no other numbers which is going to divide 3. Okay, but if I take 10, now which are the numbers that divide 10? 10 is divisible by 1, it is also divisible by 10, it is also divisible by 2, it is also divisible by 5. It has got more than two factors, isn't it? It has got four factors. So we can also define it like this. Whenever a number has got only two factors, that is 1 and itself, then it is called as prime number. If it has got more than two factors, 1, itself, and more than that, then it is known as composite number. So these are prime numbers: 2, 3, 5, 7, 11. 9 is not a prime number because 9 is divisible by 1 and by itself also by 3. It has got more than two factors, therefore it is not a prime number, so we call it as a composite number. Okay, so this is the difference between prime number and composite number. One important note, that number 1 is not a prime number. Okay, why? Because basically this cannot be a composite number. Why? A number is said to be a composite number if it has got more than two factors, right? Here 10 is called a composite number because it has got more than two factors. 9 is called a composite number because it has got more than two factors. But the only factor of 1 is 1 itself. There are no other factors for it. Okay, there is no other number which is going to divide 1. Okay, you should have more than two factors, only then you can call it as composite number. So this is not a composite number. It is not satisfying the condition. Okay, and similarly, 1 is not a prime number because if I consider 1 to be a prime number, then this theorem will fail. Using this theorem, we have discussed, there are so many things. Okay, the one simple thing is LCM. We can also find LCM. Okay, if I consider 1 to be a prime number, then this theorem fails. If this theorem fails, there are so many applications which will not be able to do it. Okay, so let's see. If I consider 1 as a prime number, what will happen? Once you get to know the theorem, it will be easy. Okay, so what is this fundamental theorem of arithmetic? You take any composite number, it can be expressed as a product of primes. For example, I can write this 10 as 2 into 5. So observe, this 10 is a composite number which is expressed as product of primes. What we have got here? Prime numbers in product. Suppose if I take 15, it can be written as 5 into 3. Or suppose if I take 75, it can be written as 3 into 5 into 5. You take any number, any prime, any composite number. Let's take 100. It can be written as 2 into 2 into 5 into 5. This is a composite number. What we have got? only prime numbers in product. So this is known as fundamental theorem of arithmetic. In shortcut, we also call this as prime factorization. Prime factorization of a given number. Factorization is basically expressing in terms of product. Okay, this number is expressed in terms of product, and in this product we have got only prime numbers, so we also call this as prime factorization. Okay, so what is fundamental theorem of arithmetic? Every composite number, you take any composite number, it can be expressed as primes, product of primes. Okay, this is fundamental theorem of arithmetic, and this representation is unique. Okay, what do I mean by unique? If I take 100, the only possibility, the only way that I can write 100 in terms of prime is only like this: 2 into 2 into 5 into 5. That is, I've got two 2's and two 5's. Okay, maybe the order might change. I might write it like this: 2 into 5, 5 into 2, or 5 into 2 into 2 into 5. I might change the order in which they appear. I might change the order in which they might appear, but the only prime numbers for 100 is only these. Apart from this, I can't have any other thing. Okay, let's take 10. It is only 2 and 5, isn't it? Can I write 3 5s as 10? There is no possibility at all. So maybe I can write it as 5 into 2. Doesn't matter. I might change the order, but this 10 can be written as 5 into 2 or 2 into 5. Meaning the prime numbers involved are only 5 and 2. Other than this, it cannot be anything. 75. Which are the prime numbers that are involved? 3, 5, 5. 1, 3, 2, 5. Other than this, there is no other number. Okay. Now let's come to this thing where why 1 cannot be considered as a prime number. If I consider 1 to be a prime number, see what happens. This 10 can be written as 2 into 5 into 1. Isn't it? 2 5s are 10, 10 1s are 10. Or I can also write it as 2 into 5 into 1 into 1. Or I can also write it as 2 into 5 into 1 into 1 into 1. Or I can also write it as 2 into 5 into 1 into 1 into 1. So here the uniqueness is gone. See, I might, if I take 1 as a prime number, I might write like this. Or some other person might write like this. Or some other person might write like this. Which means we are getting different prime factorization. See, but if you consider 1 as not a prime number, for me or for any other person, it will be 2 into 5 or 5 into 2. That's it. Doesn't matter with the order. But we'll have only 2 and 5 as prime number. But if I take here 2 into 5 into 1, one possibility, or 2 into 5 into 1 into 1, or the third person might write like this, the fourth person might write like this. There is a difference in representation. Okay, all the representations are not same. That is why we don't consider this 1 to be a prime number. Okay, this is a simple logic that I've used why 1 is not a prime number. Okay, at this stage, this is enough why 1 is not a prime number. Okay, now, so we got to know that 1 is neither a prime nor a composite. Very, very important. 1 doesn't belong to prime category. 1 doesn't belong to composite category also. Okay, so the prime number starts from 2, 3, 5, 7, so on. Composite numbers, you know it, right? And very interesting fact is the only even number that is prime is 2. This is the only even number that is prime. All other even numbers, you take any even numbers, for example 648, it is a even number. It is not a prime number. Why? Simply it is divisible by 2, right? All the even numbers are divisible by 2. So the only even number that is prime is 2. Okay, very important thing. Let's move on to the exercise. So let me write it out what I've explained. So fundamental theorem is every composite, let me shortcut it. Every composite number can be expressed as product of primes. Okay, then the smallest prime number, which is our smallest prime number, 2, and it is also the only even number that is prime. It is the only even number that is prime. Another important one doesn't belong to, one is neither a prime nor composite. It doesn't belong to any of the categories. Why is it not a composite? Because it doesn't have more than two factors. Why is it not a prime number? If you consider 1 to be a prime number, then the uniqueness of the theorem goes. If the uniqueness of the theorem goes, then we will not be able to solve many applications. Okay, so let's get into the exercise part, where in this exercise, using this prime factorization, we'll be finding LCM and HCF of given numbers. Okay, students, the second exercise of the chapter, first question: express each number as the product of its prime factors. Meaning we have to express the given number as prime, product of primes. The first number is 140. Okay, so the first number is 140. Okay, so in the working column, 140. Now, when I say prime factorization, we must use only prime numbers. Okay, now 2 is a prime number, 3, 5, 7, 11, 13, 17, 19, and so on. Okay, at least you have to know prime numbers till 25 at least. Okay, now which number shall I start with? Now whenever it is ending with 0, you can start with 5. Very simple logic. Whenever a number is ending with 0 or 5, you can start with 5. Okay, or the other way is, if the last number is even, if the last digit is even, the entire number is even. Okay, if the last number is odd, if the last digit is odd, the entire number will be odd. For example, 7, 8, 9, 2, 5, 1, 2, 1, 3, 8, 9, 6, 7, 2. This is a big number. How do we find whether it is even or odd? Just look at the last digit. The last digit is 2. It is a even number. 0, 2, 4, 6, 8, all these are even numbers. So the last digit is even, therefore the entire thing is even. If the given number is even, start with 2. Okay. Now here either you can start by 2 or by 5. It's your wish. Let me start by 2 itself. 2 sevens are 14, 2 zeros are 0. Again, this is a even number. I can start by 2 itself, or I can also use 5 because the last digit is 0. 2 threes are 6, 1 carry, it becomes 10, 2 fives are 10. Now observe, the last digit is 5, so let me start with 5 itself. 5 sevens are 7, obviously 7 goes by 7 itself, 7 ones are 7. Until you get 1, you have to continue the procedure. Therefore, 140 can be written as 2 into 2 into 5 into 7. To make it, observe, we have got only prime numbers here. In a simpler version, 2 into 2 is 2 square into 5 into 7. Therefore, the prime factorization of 140 is 2 square into 5 into 7. Okay. Similarly, let's take the second question. The second question is 156. So 156, the last digit is even, therefore the entire number is even. Let's start with 2. 2 sevens are 14, 1 carry, 2 eights are 16. This is an even number. So let's start with 2 itself. 2 threes are 6, 1 carry, it becomes 18. 2 nines are 18. And 39, it is a odd number because the last digit is odd. Therefore, I can start with the next prime number. After 2, it is 3. Is it divisible by 3? Yes, it is very clearly divisible. 3 ones are 3, 3 threes are 9. 13 itself is a prime number. So 13 ones are 13. Therefore, 156 can be written as 2 into 2 into 3 into 13. Therefore, 156 can be written as 2 square, because 2 into 2 is 2 square into 3 into 13. This is the prime factorization of this. You can have interchange. 3 coming first, 2 square in the middle. Doesn't matter with the order, but you should have only these 2 square, 3 and 13. Only these 3 things should be there. Okay. The next thing is, third one is 3825. If I'm not wrong, let me cross verify the question. Yeah, 3825. Okay, 3825. Now the last digit is ending with 5. So let's start with 5. 3825. Let's start with 5. 5 sevens are 35. 3 will be carried. 5 6 are 30. 5 5s are 25. Again, the last digit is 5. So let's start with 5. 5 ones are 5. 2 carry. 5 5s are 25. 1 carry. 5 3s are 15. Okay. Now, the last digit is not even. Therefore, the entire number is not even. So I cannot divide it by 2. By 3, let's check. What is the divisibility rule? You have to add all the digits. 1 plus 5 is 6. 6 plus 3 is 9. The answer that you get, is it divisible by 3? The answer that we got is 9. Is it divisible by 3? Yes, it is. Therefore, this entire number is divisible by 3. Okay, you have to add all the digits. The answer that you get, if it is divisible by 3, then the entire number is divisible by 3. For example, let's take this. Let's take this itself. Okay, 1 plus 5, 6. 6 plus 6 is 12. So 12 is divisible by 3. Therefore, this entire number is also divisible by 3. You could have started with 3 itself. Okay, this is how we check. So 3 5s are 15, 3 1s are 3. Again 51, does it go by 3 tables? 5 plus 1, 5 plus 1 is 6. 6 is divisible by 2, sorry, 6 is divisible by 3. Therefore, you can divide by 3. So 3 1s are 3, 2 carry, it becomes 27, 3 7s are. 17 itself a prime number, 17 1s are 17. Therefore, 3825 can be written as, you got 5 2 times, so 5 square, 3 2 times 3 square into 70. Okay, this is our fourth question. Third question. The fourth question was 5005. So let's start with 5005. Okay. Now what do we start with? This is a, this number is ending with 5. So let's start with 5 itself. 5 ones are 5, 0, 0, 5 ones are 5. Okay. Now your 1001. Okay. Now this, is it divisible by 2? No, because the last digit is not even, so it is not divisible by 2. By 3, let's add 1 plus 0, 0, 0 plus, sorry, 1 plus 0, 1. Again, if you add everything, you get 1 itself. 1 plus 0, 1, 1 plus 0, 1, again 1 plus 1 is 2. We get 2. I'm sorry, I said 1. It is 2 actually. If you add all the digits, you get 2. And this 2 is not divisible by 3. Therefore, the entire number is not divisible by 3. 2 is not possible. 3 is not possible. 5 is not possible. The next prime number is 7. So check it out with 7. 7 ones are 7. 28. Okay, let me check it out. 7 ones are 7. 3 carried, so it becomes 30. 7 fours are 28. 2 carried becomes 21. Yeah, it goes. 7 threes are, so 143 into 7. Okay, this is how you check. So basically what I did was I checked with 2, not possible, with 3, not possible, with 5, not possible. Then I'll check with 7. If 7 is also not possible, then I would have gone with 11. So order wise, one after the other prime number, you have to check it. Okay. Now 4 plus 1, 5. 5 plus 3, 8. Not divisible by 3, not by 2, not by 5. By 7 also not possible. By 11, 11 I guess it is possible, right? After 7 it is 11. 11 it is possible. 11 ones are 11. 3 carry, 11 threes are 33. Now 13 itself is a prime number. 13 ones are 30. So you have to check one after the other. Is it divisible by 2, by 3, by 5, 7, 11? You have to check it. Okay. So 505, 5005 can be written as 5 into 7 into 11 into 13. So this is the prime factorization of the given number. The last question, I'll give it as a work. Try it out by yourself. The last question of this main, that is 7429. Try it by yourself. Okay. Now, the next question, find the HCF and LCM of the following pairs of integer and verify that LCM into HCF is equal to product of the two numbers. Okay. First, we have to find the LCM and we have to verify a relationship. Okay. Let me talk about this relation, that is LCM of two numbers. Let's say A and B are two numbers. LCM of two numbers into HCF of two numbers, it is actually equal to product of themselves. So say suppose you are finding LCM of two numbers and HCF of two numbers, same two numbers, okay, and you multiply that, that will be actually equal to A into B, okay. For example, simple question, if I take LCM of 2 comma 4 into HCF of 2 comma 4, LCM of 2 comma 4 is 4, okay, LCM of 2 comma 4 is 4 and HCF of 2 comma 4 is 2. If I multiply, I get 8. If I multiply the numbers 2 and 4, even then I get 8. That is the result. So LCM into HCF is actually equal to product of two numbers, and this is applicable only for two numbers. You cannot do it for three numbers. That is LCM of A comma B comma C into HCF of A comma B comma C is not equal to A into B into C. You cannot do it like this. LCM of three numbers, HCF of three numbers is not equal to product of themselves, okay. Only for two numbers, you find LCM of two numbers, find HCF of two numbers, multiply, you get an answer. That answer will actually be equal to A into B, the product of the numbers itself, okay. So we have to find the LCM and we have to verify this relationship, okay. Let's start with the first question. The first question, we have to find the LCM and HCF of 26 and 91, okay, and we have to verify the relationship, okay. So the first question is 26 and 91. Now here the very first step is we have to prime factorize the given numbers. So the given numbers are 26 and 91. Let's prime factorize them, okay. So in the working column, 26, this is an even number, so let's start with 2. 2 1s are 2, 2 3s are 13 itself is a prime number, so 13 1s are 30. Therefore 26 can be written as 2 into 13. Now similarly 91, this is not an even number because the last digit is odd, therefore you cannot divide by 2. By 5 it is not possible, by 3 also it is not possible, because 9 plus 1 is 10. 10 is not divisible by 3, so 2 not possible, 3 not possible, 5 not possible. Let's check with 7. 7 1s are 7, 2 carry, it becomes 21. 7 3s are 21, okay. So the 13 itself is the prime number, so 13 1s are 13, okay. So here 91 can be written as 7 into 13, okay. So the very first step is you have to prime factorize the given numbers, which we have done it, okay. Now to find the HCF and the LCM, okay. How to find HCF and LCM, okay. Now to find HCF, you have to choose the common prime number in both, the same prime number in both with their least powers, okay. So HCF, same prime numbers or common prime numbers, let me write it as common. The trick to find HCF is common prime numbers with their least powers, okay. In this example there is no problem, okay. Let's look into different problems. You will understand what do I mean by least powers. Actually there is no power, there is only power 1 for everything. So LCM will be all the different prime numbers, involved with their highest powers. So when is LCM, for the least it is highest power, for the highest it is the least power, okay. The opposite. HCF we have to take the least powers, LCM you have to take the highest power. Now look at the definition. How do you find HCF? Common prime number, which is a number that is common for both 13, okay. So the HCF will be 13. Now if I've used the word common prime number with their least powers. For example, say suppose you had 13 per 1 here, 13 per 2 here. Just imagine, okay, forget about this. You had 13 here and you had 13 square here. So which is the common prime number? It is actually 13. You got 13 here, you got 13 here. And among 13, which is the least power? 13 power 1. So 13 power 1 will be your LCM. Suppose you add here 13 power 2 and 13 power 3. Which is the common prime number? The common prime number is 13. What is the least power in it? 2. So the HCF will be 13 square. I hope it is clear. Okay. So here in this case, we add only 13 and 13. This is also 13 power 1. This is also 13 power 1. Therefore, the HCF will be 13 power 1 itself. That is 13 itself. Okay. Now, what is LCM? We have to take all the different prime numbers involved. So here, which are the different prime numbers? 2, 7, and 13. These are the prime numbers, right? How many prime numbers are there? Three different prime numbers, 2, 7, and 13. You have to take the highest powers. So 2 power is 1 itself. 7 highest power is 1 itself. 13 highest power is 13 itself. So 2 into 7 into 13. So 2 into 7, 14. 14 into 30, 140, 192, if I'm not wrong. So LCM is 192, HCF is 13. A very easy one, simple. Prime factorize it and follow these two rules to find HCF and LCM. Let's do 2 more problems. We'll understand much better. Okay, the next question, 5, 10, and 92. We have to find the HCF and LCM of 510 and 92. Okay. So let's do that. 5, 10, and 92. Let's prime factorize 510. So we can start with 2 because the last digit is even. 2 2s are 4, 1 carry, 2 5s are 10, again 1 carry, 2 5s are 10. So we can start with 5, 5 5s are 25, 5 1s are. This goes by 3, 3 1s are, 3 7s are. So 17 1s are 17. So 510 can be written as 2 into 5 into 3 into 17. Okay. Now similarly 92. It's an even number. 2 4s are 8, 1 carry, 2 6s are 12, 2 2s are 4, 2 3s are 6. 23 itself is a prime number. 23 1s are 23. So 92 can be written as 2 square because 2 has come twice into 23. Now to find HCF, which is the common prime number? It is 2. Here also you got 2. Here also you got 2. Which is the least power? Here you got 2 power 1. Here you got 2 power 2. So 2 power 1 will be the LCM, that is 2. So LCM, you have to consider all the prime numbers. Which are the different prime numbers? You got 2, you got 5, you got 3, 17, and 23. Isn't it? These are the different types of prime numbers that are involved here. Okay. Among 2, which is the highest power? 2 square. So you have to take 2 square. 5, the highest power is 1. 3 highest power is 1. 17 highest power is 1. 23 highest power is also 1. Okay. Just for your reference, I'm writing it over here. Okay. So multiply all this. 2 square is 4. 4 into 5 into 3 into 17 into 23. So 4 5s are 20. 20 into 20 into 3 is 60. Okay. Let's multiply it. 20, 60 into 17 into 23. You multiply all these numbers, you get the LCM. Okay. So this is how you find the HCF and LCM. So similarly, let's solve one more problem. 336 and 54. The next question is 336 and 54. And one more thing, we actually had to verify the relationship, right? The LCM, you multiply the numbers 510 into 92, you get an answer. This is your A and this is your B. A into B, you get an answer. The HCF is 2. LCM, whatever you get. Okay, let me do it quickly with the help of the calculator. 60 into 17 into 23. So you get 23460. 23460. This is the LCM. So let's multiply HCF and LCM. 2 into 23460. So it becomes 0, 12, 9, 6, 4. You get, if you multiply these two things, you get 46920. Let me multiply these two things. 510 into 92. Even then we get the same thing. We have to get the same. So as I told you, the product of the numbers, you multiply, you get an answer. Multiply their HCF and LCM, you get the same answer. This is the result that we were talking about. Okay, the next question that we have got was 336 and 54, I guess. Yeah, 336 and 54. Let's quickly do that. So the third question, 336 and 54. Let's prime factorize 336. We have to start with what? 2, because it's an even number. 2 ones are 2, 1 carry, it becomes 13. 2 6 are 12. So we add 13. 13 minus 12 is 1. So 1 is carry. 2 8s are 16. Again by 2 tables. 2 8s are 16. 2 4s are 8. 2 4s are 8. 2 2s are 2 2s are 2 1s are 3 7s are 7 1s are. Therefore, 336 can be written as 1 2 3 4. 2 is for 4 times into 3 into 7. Let me prime factorize 54. 2 2s are 2 7s are 3 9s are 3 3s are 3 1s are. Therefore, 54 is 2 into 3 cube. Now, to find HCF, which is the common prime number, if you observe, you got 2 here and here, both the case. 2 is the common prime number. Also, you got 3 here, 3 here. 3 is also common prime number. Now, take the least power. The least power is 2 power 1 and 3 power 1. Isn't it? Common prime numbers with their least powers. 2 is common. The least power is 2 power 1, 3 power 1. So 2 power 1 is 2, 3 power 1 is 3. So 2 into 3 is 6. That's your HCF. To find LCM, to take all the different prime numbers that are involved. You got 2, you got 3, and you got 7. These are the different prime numbers that are involved. Highest power of 2 is 4. Highest power of 3 is 3 itself. And highest power of 7 is 1 itself. 2 power 4 is 16. And 3 cube is 27 into 7. Multiply all these things, you get the LCM. So to find the HCF, you have to take the common prime number with least power. LCM, all the different prime numbers with their highest powers. Okay. So in the next video, let's continue with the remaining problems. Thank you, students.